Welcome back to this new video. In this video I am going to analyze Nash equilibrium, the examples of Nash equilibrium, again applications of Nash equilibrium, limitations of Nash equilibrium. So let's start with the definition of Nash equilibrium. Nash equilibrium is the most common approach for determining the solution of a non-cooperative game that involves two or more players. The concept is named after John Nash, who introduced it in his seminal paper Non-Cooperative Games in 1951. The Nash equilibrium came up with the recognition of mathematician John Nash. The definition is that Nash equilibrium is a concept in game theory that describes a situation in which each player's strategy is optimal given the strategies chosen by all other players. More formally, player I's strategy SI is the best response to the strategies chosen by the other players. Nash equilibrium provides a solution concept for non-cooperative games where players make decisions independently without any binding agreements or communication. Now, before going to analyze more about Nash equilibrium, let's consider the basic game theories. A game involves players, strategies, and payoffs. Players are decision makers in the game. Each player has a set of possible strategies, which are choices they can make. Payoffs are outcomes that players receive based on the chosen strategies, representing gains, losses, or utility. Now consider this example of Nash equilibrium. In this example, this is a 2x2 game where we have player 1 and player 2. Player 1 is indicated by the green color card, and as well as the payoffs for player 1 is also indicated with the green color numerical digits. And the strategies that player 1 have up and down, where the strategies for player 2 is left and right. Now, to find the Nash equilibrium, we have to find different strategies. Consider player 1 wants to play up. So in that case, he is going to choose 7 because 7 is greater than 5. And if player 2 wants to play based on the strategies of player 1, then he is going to choose 4 rather than 1 because 4 is greater than 1. Again, if player 1 wants to play down, then he will going to play 4, and based on the player 1's strategy, player 2 will choose 7 because 7 is greater than 5 according to this example. Therefore, we have two Nash equilibrium here, like the up and left. Again, another Nash equilibrium is that down and right. So if we can find two circles like that example, so that will be our Nash equilibrium point. Now consider another game where the payoffs for player 1 is like as before, the green color numerical digits, where and the blue color numerical digits for player 2's payoffs. Therefore, given this example, if player 1 wants to play up, then he is going to play 5 because 5 is greater than 4. At the same time, given the strategy of player 1, if player 2 wants to play, then he will play 6 because 6 is greater than 1. In the similar fashion, now if player 1 wants to play down, then he is going to play 7 because 7 is greater than 3. At the same time, given the strategy of player 1, if player 2 wants to play, given the strategy of player 1, then he is going to play 9 because 9 is greater than 2. Therefore, in this game, we have down left as the Nash equilibrium outcome. Consider another game, and the payoffs for player 1, like as before, the green colored numerical digits shows the payoff for player 1 and the blue color payoffs are for player 2. Now, given this example, if player 1 wants to play off, then he is going to play 4, and given the strategies for player 1, if player 2 wants to play, then he is going to play 5 because 5 is greater than 1. So up and right constitutes a Nash equilibrium. Now consider other points. If player wants to play down, then he is going to play 6 because 6 is greater than 5, and if player 2 wants to play, then he is going to play 5 because 5 is greater than 2. So in this game we have only one Nash equilibrium, up and right. So up and right constitute the Nash equilibrium for this game. Now consider this example finally. So we have the payoffs like as before. The green colored numerical digits is the payoff for player 1 and the blue colored payoffs are for player 2. Now if player 1 wants to play up, then he is going to play 6 because 6 is greater than 2. Again, given the strategy of player 1, player 2 is going to play 4 because 4 is greater than 3. Now if player 1 wants to play down, then he is going to select 9, and based on the strategy of player 1, player 2 is going to play right because 8 is greater than 5. Therefore there is no Nash equilibrium in this game. So the outcome is that there is no Nash equilibrium. Now, how many types of Nash equilibrium are there? Nash equilibria can be classified into two main types based on the strategies involved. The first one is that pure Nash equilibrium, and the second one is mixed strategy Nash equilibrium. Pure strategy Nash equilibrium. Players choose specific strategies with certainty. In the example above, confess shows us the pure strategy Nash equilibrium. So therefore the outcome -2 and -2 will give us the pure strategy Nash equilibrium. We have another types of Nash equilibrium like the mixed strategy Nash equilibrium. In that case of mixed strategy Nash equilibrium, players randomize over possible strategies, choosing each strategy with a specific probability. Mixed strategies are common in games where there is no pure strategy. Such as rock paper scissors example, where each player has a probability of choosing rock, paper and scissors to keep the other player indifferent to their own choice. Existence and uniqueness of Nash equilibrium. Existence: at least one Nash equilibrium will be played. Is proved that in any given game with a finite number of players and strategies, there is at least one Nash equilibrium, possibly in mixed strategies. This is known as Nash existence theorem. And uniqueness: a game may have a unique Nash equilibrium, multiple Nash equilibria, or infinitely many. The prisoner's dilemma has a unique Nash equilibrium, while the coordination game has multiple equilibria. This multiplicity raises questions about equilibrium selection, which is sometimes resolved by examining additional factors like social norms, historical precedents, or repeated interactions. Now, the applications of Nash equilibrium. First of all, in economics, Nash equilibrium is used to analyze market and competitive behaviors such as pricing strategies, oligopoly competition, and auction design. Again, in case of politics, politicians can model Nash equilibria to strategize on policy positions, anticipating responses from other parties and voters. Business strategy. Companies use Nash equilibrium to forecast competitor actions, such as in advertising, spending, product releases, and pricing. In case of environmental policy, countries can be modeled as players in an international game over resource use and emissions reduction, where a Nash equilibrium might represent a stable outcome of policies. There are some limitations of Nash equilibrium. The first one is that predictive limitations. Multiple Nash equilibria can make it hard to predict which one will occur. Non-cooperative outcomes. In some cases, like the prisoner's dilemma, the Nash equilibrium may be socially suboptimal. Rationality assumptions. Nash equilibrium assumes that players are fully rational and have more information, which is not always true in real-world scenarios. Nash equilibrium is a very powerful tool in game theory, although it has some limitations. Nash equilibrium allows us to predict stable outcomes where no player has an incentive to deviate unilaterally. Understanding this concept helps us to analyze and anticipate outcomes in strategic interactions across a wide array of fields. By considering both pure and mixed strategies, we can capture a range of players' behaviors from cooperation to competition. Thank you everyone for watching this video. We will explore how Nash equilibrium applies to repeated games and how cooperative strategies might emerge over time in our next videos.